The type of supercell you might expect to see in a given event can be forecasted ahead of time using atmospheric soundings. If you're looking through the models in the days leading up to an event, you might select a few forecast soundings in the potential area of interest to get an idea of what type of supercell you might expect to see. And this can give you at least a decent idea of how you might want to attack navigation during the chase. The diagram you see on the left here is the skew-t. This shows you the thermodynamic properties of the atmosphere. And the diagram on the right here is the hodograph. And this is what we're going to hone in on when we're trying to assess the type of supercell that we might expect to see in a given event. The hodograph is a visualization of the wind profile in the atmosphere. The wind direction and speed is plotted at every single level of the atmosphere, and the dots are connected to give you a graph that shows you how the winds are changing as you go up in the atmosphere. Each point has a speed and direction. So our origin is here, and all of these rings that you see here, those indicate the speed of the wind in knots. So for example, let's take this point right here. This would be our point at 1 kilometer. You see the 1 right there. That indicates the altitude of that particular wind vector in the atmosphere. So our 1 kilometer wind vector would look something like this. So the wind at 1 kilometer is out of the southwest, so we have a southwesterly wind at 10, 20, 30, 40, almost 50 knots. So this is approximately a 50 knot wind out of the southwest. How about our surface wind? This 0 point here, that is our surface wind. So let's draw our vector up from the origin. Would look something like that. So our surface wind is out of the south, so a southerly wind at 10, 20 knots. So our surface wind is a southerly wind at 20 knots. The type of supercell that might dominate a given environment depends on the mid and upper level storm relative winds. These modulate how precipitation is vented relative to the location of the updraft. In other words, is the precipitation pushed far away from the updraft, or does it remain fairly near the updraft? This all depends on the storm relative winds in the mid and upper levels of the atmosphere. First of all, what do we mean by storm relative? Storm relative winds are just the winds with the storm motion factored out. So it's the wind that the storm is feeling. We're experiencing the winds from the storm's perspective. All we do to find that on the hodograph is, instead of drawing our wind vector from the origin, we would draw it from the storm motion to the point on the hodograph of interest. Our storm motion is given by this black bullseye right here. This is the bunker's right-moving supercell storm motion. It's not always a perfect estimate, but it's a good enough estimate for our purposes when employing these techniques. So for example, our storm relative wind at, let's say, 9 kilometers, this point right here, we would draw our vector from the storm motion all the way up to 9 kilometers. And it can be a little bit tricky because we're not at the origin here, so we might be a little bit offset from our actual rings, but just eyeball it. So where you start would be 0. This would be about 10, 20, 30, 40, 50, about 60 knots there. So our storm relative wind at 9 kilometers is out of the southwest, so southwesterly, at about 60 knots.
Storm chasing is already tough. Learning alone makes it tougher. Discord community link in description.
For this technique, we're looking at the winds above 6 kilometers off the surface. If the majority of the storm relative winds above 6 kilometers are greater than 40 knots, low precipitation supercells will be favored because those stronger winds aloft are venting the precipitation much farther away from the updraft, making the updraft and its features much more visible. If the majority of storm relative winds above 6 kilometers are less than 20 knots, high precipitation supercells will be favored. In this case, precipitation venting will be quite poor, and therefore a lot of precipitation may shroud the updraft and its features. And if storm relative winds above 6 kilometers are between 20 and 40 knots, then you'll have a tendency toward more classic supercells, although it can depend on some other factors. In this example here, if we were to draw in vectors from our bunker's right storm motion to all of our points above 6 kilometers on the hodograph, you'll notice that they're all above about 40 knots. Again, you kind of just have to eyeball this because the bunker's right storm motion is not our actual origin, but you can just estimate it based on the spacing between each of these rings. So for example, this is our 6 kilometer vector. This is about 10, 20, 30, about 40 knots or so, maybe just over 40 knots. The 7-kilometer point is right on top of the 6. Our 8-kilometer vector, just a little bit longer than that 6-kilometer vector, so maybe about 50 knots or so. And then we've already figured out the 9-kilometer point, which is 60 knots. So all of our points above 6 kilometers are well over 40 knots, indicating that this profile would be very favorable for low precipitation supercells. Contrast that with this example here. Notice how truncated the Hodograph is in the mid and upper levels of the atmosphere. If we were to draw in our vectors for our points above 6 kilometers, notice how short they are. Here's our 6-kilometer vector, this one on the right. It's maybe about 10, maybe just under 20 knots there. The 7-kilometer vector right there, even shorter. 8 kilometers, about the same as 6. And so all of these are right about 20 knots or below, indicating that this profile would be favorable for more high precipitation supercells. The shape of the Hodograph and the configuration of the winds aloft also modulates how precipitation is vented away from an updraft. This is where veering and backing of the winds come in. Veering means that the winds turn in a clockwise direction with height, whereas backing is when the winds turn in a counterclockwise fashion with height. Because the configuration of the winds aloft modulates the dispersion of precipitation within a supercell, the Hodograph is actually going to be a pretty good proxy for the shape of a supercell on radar, and it can give us an idea of the direction that precipitation will be vented relative to the updraft. In this example, notice how the winds veer in the low levels, but then they eventually back a little bit above 3 kilometers. Again, veering of the winds with height, those winds are turning in a clockwise direction in that lowest kilometer or two, and then they turn in a counterclockwise direction above about 3 kilometers. In other words, the Hodograph bends back to the left a little bit. Now let's draw in a hypothetical supercell that matches this wind profile. So in the low levels would be our hook echo, our mesocyclone region of the storm. And above that, we would just track along the shape of the Hodograph to see where precipitation would be vented. So to start, we would veer off to the right a little bit, and then once that backing occurs above about 3 kilometers, we would turn back to the north a little bit. And that shows us that most of the precipitation is going to be vented away from the updraft of the storm. Here is your mesocyclone. Tornadic activity would be located at that tip of the hook echo, and most of that precipitation will be vented away from that area, making the updraft much more visible and any tornadic activity easier to spot, and the storm may take on more of a low precipitation appearance. Let's do the same thing for this Hodograph. Notice in this case that the winds just veer the entire way up through the atmosphere. They're turning in a clockwise direction in general, all the way up through the atmosphere. The Hodograph is essentially folding over on itself. If we were to draw in our hypothetical supercell here, notice how the precipitation is vented out in front of the mesocyclone region of the storm. Here's your hook echo. Any tornadic activity would be here, and all that precipitation is thrown out ahead of the storm and ahead of the storm's motion, which is to the northeast, potentially shrouding the updraft in more precipitation and making any tornadic activity more difficult to spot. This lends itself to more high precipitation supercell structure. Now, there is one exception to these rules, and that is the mini supercell. Mini supercells are just smaller versions of full-fledged supercells. They have the same type of structure, same hazards, but they're just smaller in size. Mini supercells by nature don't produce as much precipitation. Therefore, if you have an environment that might at first glance suggest more high precipitation supercells, if the environment also favors mini supercells, that might not actually come to fruition. The storm relative winds in the lowest kilometer of the atmosphere modulate supercell size. This is called storm relative inflow. Storm relative inflow determines how much mass is flowing into a storm. Stronger storm relative inflow means that more mass is getting pulled into the storm, and therefore that storm is likely to be larger, whereas weaker storm relative inflow means less mass getting pulled into the storm, and you get a smaller storm. A general rule of thumb is that if storm relative inflow in the 0 to 1 kilometer layer is less than 25 knots, then mini supercells will be favored. In this example, if we were to draw in our storm relative wind vectors at the 0 and 1 kilometer point, for example, you'll notice how short they are. We can actually get a direct measurement for the surface storm relative wind vector because the surface wind is right there at the origin. It's not even 15 knots. The 1 kilometer vector is a little bit longer, maybe about 25 knots or so. Both of those are underneath that threshold for mini supercells, and therefore this would be an environment that would favor mini supercells. Now, at first glance, you might think that this environment would favor high precipitation supercells. I've drawn in our 6 and 8 kilometer storm relative wind vectors, and they're very, very short, especially that 8 kilometer vector, which is not even 20 knots. But because we have such weak storm relative inflow, high precipitation supercells may be precluded because mini supercells are favored, and again, mini supercells produce less precipitation by nature. And while an environment may have weak storm relative inflow, we need to make sure that supercells are favored altogether. That usually means either 0 to 6 kilometer shear or effective bulk shear is about 30 knots or greater. And really this goes for all of the supercell types. Of course, we need to make sure that we have a supercell-favorable environment in the first place before making these assumptions about supercell type.
Remember to check out those links in the description below, and then watch another video.